Yeah, I actually wanted to extend my talk on the ZK-CNN. Yeah. Thank you. Thank you, guys. I actually wanted to extend my talk on a ZK-CNN, but my knowledge on ZK seems to be meager to talk to you. So I instead got interested into the neural network on an edge device. So the narrative is that the limitation of machine learning on the ZK and machine learning on the iPhone or the Apple Watch is strikingly similar because the computation resource is very limited, and you want to minimize the computation overhead so that it runs on the edge device with a very limited computation power. So in the traditional So in the traditional neural network, probably the most common operation from the fully connected layer, maybe there are many layers. The most common operation is a matrix multiplication, and that is probably why the neural network is suffering in ZKML. It's because matrix multiplication with the vector against the weight matrix plus the bias, which becomes essentially the next output for the next layer. This computation itself generates around V times W amount of multiplication. And normally the model size is becoming sorry?
What's W?
Oh, it's weight. Sorry. Bias.
Oh, bias.
And output. And this should be vector, which is also an input. Yeah, so the time complexity of this matrix multiplication is V times W. And W can be very large. And also the V tends to be like, nowadays it's like probably like 2 to the power of 10 floating point numbers. And the limitation, the thing that makes the ZKML so difficult is because first of all, floating point is not native in modular arithmetics. And second, matrix multiplication generates a lot of So first, the floating point is not a native way of representing a number in modular arithmetics, which is like the building block of the ZKML. And the second, matrix multiplication generates too much multiplication operation, which is also an overhead. So due to this, the CPU or GPU now have much more computation power. So this has not been something that was presented like in modern times. So this concept of like weightless neural network was actually investigated or researched back in 1990s or 1980s when the CPU was very, very limited. And it's coming back because like people want to use a machine learning model in their edge devices, such as your watch or an iPhone. And that is why I'm going to present how weightless neural network works. So, okay. So I think it's better to start with a very concrete example called MNIST. I don't really know what it stands for, but what it essentially does is there's an image that says, that has some number from 1 to 9, or 0 to, oh, I think it's 0 to 9. The task of the training data set and evaluation data set is to recognize some scribbly numbers into, this is like 1, and this is 2. So you have to classify very cryptic looking numbers into the actual numbers. So if you actually get to see how the data set looks like, the 1 to 8, the training data of this data set seems like pretty hard to read, and it's been a challenge for the model, for the machine learning practitioners to build a model that recognizes what actually the number corresponds to. So, so given this data set in weightless neural network, so say you have a cryptic number which looks like an ampersand, but you want to encode this into a bit. So it's gonna be 11101. So it's.
Is that a bitmap, something like that? Bitmap, the image.
Yeah, it's a bitmap. Yeah, it's a bitmap, so you can always map into a string of binary integers. So, and then you build a RAM where this binary string becomes an address in the RAM. So if you input this number into the RAM, it's going to output some, it's going to record somewhere in the RAM that this value exists. And the other ones is just going to be mere zeros. And if you input more of the training data set, like 7, 111, 0, 0, 1, 1, which is also going to wrap into a value in the RAM. So if you show like 5,000 images to the RAM, it's going to have some numbers in the RAM that has, which is an activated value cell, which records that the model actually saw these numbers in a training data set.
How to decide the position that you want to put in the RAM?
Oh, so it is exact. Oh, sorry. So it is exactly the same as how the RAMs work. So it's just a lookup table for all the bit strings. It's
bit string is a string, right?
Mm-hmm.
The number for that is only 1.
So
What is N? N is the length of the string.
yeah. And the size of the RAM is 2 to the power of n. And how it lookups is probably, like, if you see the first number is 0, then you take this path. If it is 1, you take this path. So the whole RAM consists of like address to value. So this becomes an address, and the RAM becomes like a storage of the number that corresponds to the address.
I see.
Mm-hmm. Good so far?
Yeah.
Yeah. So
Why is it called weightless?
so it doesn't really contain any weight that actually computes a matrix multiplication. It only just remembers the training data set that actually seen during the training. So how the training works in the weightless neural network, you just have to input all of your images into the RAM and see if the value exists in the RAM. And
Would it happen that if you input just one instance there in the RAM, RAM, there will be 2 or more bit flip from 0 to 1. You just give the example that for each input there is 1 in the memorized in RAM.
Mm-hmm.
But will it happen that
Like duplicate training data?
yeah, for example, no, just one example,
Uh-huh.
but triggered 2 bit flips. Is that possible?
No, because you have like 2 to the power of n storage cells. And that's why you can always like encode into just one number. Because
okay.
yeah.
Okay, the 2 to n is not the column, number of column, it's actually the number of the RAM. Okay.
Yeah. So this RAM has 2 to the power of n cells for every bit. The problem about this, and so MNIS is 28 times 28 bitmap image. This is, I don't know, like 768. Not sure about it, but this is how big it is. So if the n is 768, it's going to be 2 to the power of 768, which is probably larger than the number of stars in our universe. So this is not really a viable solution. So what instead it does is, so you want just to pick like some random numbers, random bits. So position from like here, or here, or here. So it shrinks the size of the bit string, picking randomly using some random function. So say, just for a very simple example, you pick from the third, probably from the fifth, maybe it's 0. And this also becomes, I'm just making some weird examples. So this number 8, the image of number 8 from the MNIS dataset is represented to the bit string initially. And then you pick some random bits from the bit string, which you encode to a smaller vector. And now if you try to find this number, this bit string in a RAM, the size would be 3. And then you're going to have some numbers that don't really take too much space in the RAM. And how this generalizes is because if you have sufficient training data set, for example, you have a very similar image that looks like this, and the patterns of the bit string is going to look very similar because, you know, it's the same 8. It might differ by bit, but like, if you actually choose wisely using the random functions, it might result into the same bitmap, the bit string address. So say there is like a new 8 coming into this into the network, it's going to encode into the same function, the same bit string. And if you query that number into the RAM, it's going to say, oh, there is a value which is going to say this is part of 8. So maybe this is just like a very simple conceptual architecture how the RAM-based and bit-string-based recognition works. So just to give you some more knowledge about how the classification works is So you first encode this 2 into a bit string using the random function, selecting only the bits that you're interested to. And you show this bit string to the second RAM only, so that the second RAM is the only RAM that remembers such bit string. And this happens for all the numbers in the training data set. And if you, for generalizing, so if you input like 8, so you input this number or a bit string representation into a RAM, so only the RAM that has this value is going to be activated. So this is summed so that, and this is argmaxed.
How do we determine which RAM should the number to put in?
Oh, so this is for training data. So for training, you put the 2 only to the RAM that you're interested into. If you're doing inference, you just put every numbers to every RAMs. So if you input the 8 into the second RAM, it's not going to activate anything, because it is very unlikely that it has this kind of pattern in the RAM. So that's why you need to argmax the probability or the activation count of the RAM. Yeah. And so this is yet probably a good optimization, because we went from a 2 to the power of n, and we picked only a subset of n. Let's say that's only 2 to the power of m. But this is like very, it leads to an explosion of the state, because say we already have like 768 n, and we probably choose like 100 or like 50, which is still a very large number. And the further technique to optimize this is to use yeah, so it's actually hash function. So I thought when I read this paper, I thought it would be good for the crypto people. It has a lot of like lookups and hash functions and like RAM whatever, because it's more friendly to you. So I just picked this paper for that purpose. So say if there is an 8, you put this into a Bloom filter. Have you heard of a Bloom filter? Yeah, it's the same Bloom. Is it the same Bloom filter in the? Yeah. So what it does, it has a multiple hash function. And it hashes into a result that's saying whether this 8 is a member of this collection of classes which corresponds to 8. So it's like Bloom lookup with some probability included into it. And if you choose the hash function wisely, because hash function is really good, because like most of the bits in the bit string is actually very sparse. And this hash function serves as a purpose that intellectually, like wisely select like very relevant or like feature heavy bits to be encoded into a much smaller form. So this is how the Bloom filter works. So if you replace the RAM by a Bloom filter using some specified hash function, say this all becomes a Bloom filter. And it becomes some probability, like saying 1 or 0 or 0.9, like 1, 0. And you pick. So if you actually Bloom filter this training data or or the image into this filter, then you're going to have some activation counts from the hash function, and then that number of activation count is going to be the determining factor for the class. So you determine class from here using this argmax again.
So is the argmax for inference?
Yeah, it's for the inference. So yeah, that's how the weightless neural network works. And there are some more techniques, because this might also cause some overfitting, because if the training data is provided once, and this one time scene problem, so you input like 8 into the Bloom filter, and it corresponds to some value, and this value might be very biased into like one training example, which also causes overfitting of the model. And so for that, you also use a bleaching. So it waits for like B number of activation threshold, so that it prevents overfitting. So that's how the weightless neural network works. And this is very, I think it's building a circuit out of this is probably pretty cheaper than implementing all the matrix multiplication or CNN or whatever, because now it's all modular arithmetic friendly. It's all in circuits, as you can see, and you just have to implement the hash function so that it just activates some elements in the RAM.
Is it used in ZKML right now, or?
It's not. It's not.
Okay.
Yeah.
So you are a new idea, right?
So I saw it from some like Twitter articles. Like someone said about this. Maybe this WNN, weightless neural network, might be very efficient for the ZKML.
Okay.
Yeah.
I see.
There is actually a team implementing this in ZK. It's called Zero Gravity. I think they ranked first during the this ZK hack.
Oh, okay. I actually heard this from Kathy in his Twitter post. So yeah. So this is how the weightless neural network works, and yeah, without like super hard matrix multiplication. Yep.
So I think generally those big AI experts, they think that with this lookup, it could be much quicker than using a neural network, but the accuracy sometimes doesn't look good.
Yeah.
So say implementing this, how practical or useful do you think this will be? Like if we're using this for AI.
So I think the most inefficient part is probably trying to encode an image into a bit string. So there needs to be some way to like compress the size of the bit string. And if there is a smart way of implementing that into a circuit, probably it might serve as some alternative to the neural network, which is matrix multiplication based into this lookup tables. But to be honest, so it's just using some hash collision on the hash map just to hack into finding some duplicate values within the network. So naturally it requires a lot of training data so that you can have like valid amount of training data. And also if you have too much training data, it might just saturate the RAM, and it's just going to say like whatever that activates here. It's like activation count is going to be near to the 1, which is not really the same in classical neural network, which has a premise that if you have like a lot of training data, it's always going to improve, but it's not true here. But So if you're just trying to use a very simple state machine that that allows some very simple classification or like linear regression, I think this way might be an alternative for the ZKML to use. But it's from the 1984. So yeah, it's ancient. Yeah.
I think it's GKR friendly, you know.
Is it?
Yeah, the training process is GKR friendly.
Okay. Yeah.
And then for the this part is just like naive sum lemma. I mean the argmax. It's just a summation to us as a map, right?
Yeah. So it's not it's
It's a different way to buy sum check.
is it?
One layer sum check.
Oh, okay. Just one layer and just
So there is no summation in argmax, right?
yeah, it's not really an argmax. It's more like just get the index of the maximum value in the vector.
Okay.
Yeah.
Okay. Alright.
That is argmax, but there is no sum, right? It is just argmax.
So the summation is probably here for the activation count.
Okay.
Yeah. So it can be like 8 or something. But
What exactly argmax? Can you
argmax? Argmax is max x1 max x2.
See, that is argmax is the index of the maximum, right? Not the max.
Yeah. Yeah, you're right. You're right. So yeah, I was just trying to explain. Yeah.
Just put IND in front.
Yeah.
Very good idea.
Yeah.
Like exactly, yeah, from
I don't know how to express this in math, so you get the point.
So if you have an array, argmax is the index of the array of the element of the array which is the maximum.
maximum.
Yeah, yeah.
The index. Not
The index, not the maximum value.
Okay, that's not it's not really friendly.
Yeah.
Max. But maybe we can use another.
Lookup.
So the ZK friendly words here is lookup, hash, and bloom. So I
Bloom is just a hash, right? It's a
yeah, it's a way of knowing if some value is within the set or not. Yeah.
That hash part can be used in the lookup table.
Yeah, right. So it's lookup. So this is machine learning lookup. Thank you.